Transport process. What we have been discussing in the last class was electrokinetics. I mean, near the end of the last class we started this topic of electrokinetics. What we had on this PowerPoint slide here is by electrokinetics what we mean is interaction between solid surfaces, ionic solutions and macroscopic electric field. Okay, and there are two types we have investigated in the or we have discussed in the last class. One is electrophoresis and other is electro-osmosis. We started with this electro-osmosis and we will get back to this electrophoresis. Both are manifestation of electrostatic component of the Lorentz force on ions and surface charges and Newton's second law of motion that we have already discussed. Electrophoresis, we will come back to this later. Electro-osmosis is basically a motion of electrolyte liquid with respect to fixed wall due to electric field applied parallel to the surface. So, what we mentioned in the last class is that when there is a solid surface and an electrolyte next to it, electrolyte dissociates, there is a dissociation of positive and negative ions, and there would be acquiring of surface charges on the solid surface. So, solid surface acquires surface charge when brought into contact with an electrolyte liquid due to various reasons. One was differential adsorption of ions from electrolyte onto solid surface. The second is differential solution of ions from the surface to the electrolyte, and the third is deprotonation of or ionization of surface groups such as surface silanol group of glass or silica. So, what we have is SiOH on the surface that breaks down into SiO minus and H plus, and H plus goes to the solution, and so there is a charge developing on the surface. Deprotonation is most common, and depending on the pH of that solution that you have on the surface, there would be a net surface charge density at the liquid solid interface, which is a function of local pH, and you can expect full deprotonation to occur at pH greater than 9. This we discussed in the last class. What we had as a so the immediate effect of this is ions of opposite charge in the electrolyte are attracted and the like charges are repelled. That means, what we had discussed in the last class is if there is a surface, then there would be some charge developing on the surface, and I said that these charges would be existing up to a distance, maximum is 0.2 nanometer to the depth of this solid material, and these charges will be attracting the opposite, the counter ions. So, the counter ions would be attracted. Now, these counter ions, there would be a very thin layer of these counter ions which would be adsorbed on the surface, okay, apart from various neutral molecules which are also at the same time being adsorbed on the surface. So, there would be the counter ions, there would be a compact layer of counter ions next to the surface, immediately next to the surface. This thickness is pretty small, and there would be a diffused layer of counter ions. Okay. So, there would be some co-ions also present, but it is predominantly the counter ions. So, this is basically a diffuse layer of counter ions that would be existing at the same time, and these counter ions can be pooled by putting an electrode here and here and applying a positive charge. So, if these acts as an anode, that means, if you put a voltage across these two electrodes, then automatically these negative charges will be pulled to one electrode, and by that way there would be ion drag possible on the fluid that is existing on the channel, and by that method the fluid will start moving, because as I said in the earlier class also, that in the Navier-Stokes equation there would be a body force term arising from the this ion drag. So, this is something which we referred as electro-osmosis. So, what we discussed in the last class, quickly through this PowerPoint slide: ions of opposite charge in the electrolyte are attracted and the like charges are repelled. The net excess of mobile ions near the interface with charge with the charge that is opposite to that of the wall is referred as electric double layer. Okay. These excess charges can be used to impart a force on bulk fluid through ion drag. That is exactly what I mentioned here. Now, counter ions reside in compact layer next to the wall, which is referred as Stern layer, and these counter ions reside in adsorbed state. Adsorbed state means these counter ions are not available for mobility, not available for flow. On the other hand, there would be a diffuse layer of counter ions that reside in more diffuse layer next to the wall, that is up to a distance away from the wall, that is referred as the counter ions counter ions that reside in more diffuse layer next to the wall. These ions are free to move. Now, so we had talked about something called a Stern layer. We had talked about something called a Stern layer, where there is this adsorption and these are pretty much mobile ions, and there is a diffuse layer. Okay. There is a scientist by the name Chapman. There is some contribution from him. So, this layer also is referred as this diffuse layer, also there is some name attached to it. Now, if we try to find out what would be in the last class, we mentioned that our aim is to find out what would be the concentration profile if we call it C plus and C minus, if we call it C plus and C minus as a function of Z. Okay, what would be the concentration profile as a function of Z? Okay, so that is what is important to us at this point. So, that means how the concentration will change with Z as you go. Z is what? Z is the distance from the wall in this direction. So, in this direction the distance from the wall is given as Z. So, what would be the positive ion concentration and the negative ion concentration as a function of Z? That is what is of primary importance to us, because once we find that, then we can think of the body force these ions can apply. Okay, so, before we get to that, so we have to establish what is the functionality for C plus Z and C minus Z. Now, if somebody plots, if I try to plot, if this is Z and this is say concentration. Okay, so let me put it this way. Say this is the C0 that we have. What is C0? C0 was the concentration to start with. There was that means C plus is equal to C minus is equal to C0 to start with. So, at infinity or at farther, so at wall is here, Z equal to 0, this is the wall. So, at away from this, far away from this, at infinity, what would be the C plus and what would be the C minus? They will fall on C0. All right, you think of this, you have NaCl. Now, NaCl has been dissociated into Na plus and Cl minus. Okay. So, Na plus and Cl minus. Now, this Cl minus has been attracted to the wall and Na plus has been repelled. Okay. But the concentration of Na plus and Cl minus, they will be uniform at bulk. They will be same at bulk. So, that means these C plus and C minus, they will approach this value C0 at Z equal to infinity, or not infinity, Z is equal to some substantial value which you consider as bulk, which is not next to the surface. So, that is the value. Now, what would be the C plus ion concentration or C minus ion concentration near the wall? If we follow this particular picture, we expect the C minus to be more and C plus to be less than C0 near the wall. Am I right? So, that means you can expect a plot something like this and a plot something like this, both are merging to C0. Now, one is for C plus and other is for C minus. As per this picture, which one is what? The bottom one is C plus, okay, bottom one is C plus and the top one is C minus. All right. So, this is the function, this is what we expect here, and what we need to know is how do we give a functional form to this. See, because how do we theorize this? I mean, I can understand intuitively the concentration will change like this, okay, but how will we put together a functional form for this? C plus is equal to something e to the power minus Z, etc. So, we have to come up with some kind of functional form, and for that I need to understand what the governing equations are. So, we have to get into this governing equation and boundary condition, so that we can give a functional form to this concentration profile. Now, here I must mention that we have to resort to this term called chemical potential, which we will be defining as mu. Okay. So, in fact, I mean, since we will be talking about this Navier-Stokes equation as well to find out what would be the ion drag at a later stage. So, that time viscosity we will define as eta for these analysis. So, because chemical potential it is defined as mu. I mean, those you must be having sufficient background of thermodynamics, you know that how chemical potential it is defined by mu. All right. Now, I put here one expression. I mean, I do not have I mean, I cannot give the derivation of it here, but you have to accept what I say, but I can tell you what is the origin of this expression. No, I started at a wrong place. It's, I mean, okay, I use another page, don't worry. This is an expression for chemical potential where we have this plus and minus charges, that means these ions are available, and here these mu 0, this here I have a mu 0 term which is basically the chemical potential in absence of an electric field, chemical potential, this is chemical potential in absence of electric field, and this C 0, this C 0 is the concentration, or I would say this C 0 is the ionic density, let us call it ionic density. Okay, ionic density in absence of electric field. And what is this electric field? This is the electric field that we are talking about, phi r. R is just a position vector. Okay. This z is, do not confuse this z ever with the small z that we have. So, to differentiate this, I mean, I put a mark here, this is a I mean uppercase z. This uppercase z is basically the what should I say, the valency. This z would be 1 for NaCl, this z would be 2 for CaCl2, it is that way. Okay. So, that is the value of this z. So, z would be the valency number, and this E is the elemental charge. E is called the element or elementary charge. Elementary charge, basically what this means is the charge of an electron. Charge of an electron, its value is 1.602 into 10 to the power minus 19 coulomb. Okay. So, this E is elementary charge. These, now what do you have? We have this T, which is absolute temperature, I am not writing it, you know what T is, and Kb is Boltzmann constant. So, Kb is Boltzmann constant. I have already given you the value of Boltzmann constant before. So, I do not write it here. Now, what you have here is what we have here is this chemical potential. This is constant throughout a system. That is something which we have to honor. Chemical potential is constant throughout the system, constant throughout a system, throughout the system. This equation that I have written here for plus and minus, this if you write it as plus, then this should be plus, if you write it as minus, then this should be minus. That is the idea of this expression. Okay. And this function r, I mean, do not confuse this R later on we will write it in terms of z. Z is the Z is the distance away from the wall. Okay, so that is what is Z. Now, this R is a general position, the general coordinate system. So, that is why it is written as R. Now, this expression comes from the fact that chemical potential can be written as the derivative of free energy, basically del G del N at constant pressure and temperature. You must have seen this expression in connection with chemical potential when you studied thermodynamics. So, this is the origin. I mean, this is the place from which this expression can be drawn. I am not getting into this. I am not getting into this, but you can refer thermodynamics book to find out how we can arrive at this expression. So, this is basically the guiding expression for these ionic or charge profile above the surface. Now, what you have is, since I said that chemical potential is constant throughout the system, this you have to honor. So, what you have to write is delta of mu plus minus r, this has to be equal to 0. That means, the derivative of this mu, that has to be equal to 0. What that means is, if you utilize this expression, what you get here is this is the expression that you get. If you have the grad of mu is equal to 0, then you get this as the expression. Next, what you do is you have a boundary condition. Let us write down the boundary condition here. The boundary condition for this C plus minus at Z is equal to infinity, that is equal to C 0, that we have accepted that at the bulk the co-ion and counter-ion concentration, they are equal, and that is equal to the C 0. Okay. So, you can use this boundary condition and you can come up with an expression for which will appear like this. You will come up with an expression for concentration profile which will appear like this. Now, if we write the, if we define a charge density, which is, I mean, for a general case, this charge density is defined as rho EL, which is equal to summation of I is equal to 1 to infinity Ni Zi into E. Okay, that is all the types of charges that are possible here, but here in this case, since it is a symmetric electrolyte, for a symmetric electrolyte, the charge density is written as Z E C plus minus C minus. So, that is the charge density that you can write. Ideally, for all charges you need to sum them up, but since these are equal, since this is a symmetric electrolyte, that means NaCl breaking dissociating into Na plus and Cl minus. So, so it is a symmetric electrolyte. So, C plus, so it would be C plus R minus C minus R. So, in that case, if you bring in this expression that you already have for the concentration profile, if you bring in this expression, what you get is that rho ELR, this is equal to minus 2 ZE C0 sin hyperbolic ZE divided by KBT into phi r. How are you getting sin hyperbolic? Because it is e to the power minus something plus e to the power plus something. What is this e to the power? Here we have this expression. All right. Here we have this expression, and here we have e to the power something. So, for minus sign it is e to the power minus and then e to the power plus. So, you end up with this expression for charge density, which is equal to this quantity. Now, this charge density is something which is important to us in Navier-Stokes equation, because if we try to write the Navier-Stokes equation like this, derivative with respect to t plus those convective terms, that is equal to the grad of p plus, I said that viscosity has to be written in terms of eta and not mu, plus if you have a hydrostatic head, plus this is the body force term arising from this ion drag, and this is given by rho EL into E. So, this is the Navier-Stokes equation that you need to solve if you have to find out what would be the velocity profile, what would be the velocity profile in this case, in this, if you have an anode and a cathode, and if you have these ions being dragged. Okay. So, then in that case you need to solve this Navier-Stokes equation, where this rho EL term, this is primarily operational. So, if you do not give a pressure, if you do not, if your inlet pressure and outlet pressure, if they are same, if delta P does not exist there. So, in that case it would be just, for a steady state case, it would be just an interplay of this term and this term. All right. So, this would be an interplay between these two terms, because obviously, if the viscosity is more, then it would be difficult for the fluid to be dragged by ions. So, it would be an interplay between these two terms, and that will define what velocity you get for electroosmosis. All right. So, this is how this rho EL is coming into picture, and that is what we are trying to find out. Okay. Now, we will get to this Navier-Stokes equation a little later. However, let me get some more feel of these, what are these individual terms. Okay, let us first see what is E. E is the electric field in continuum hypothesis. In fluid mechanics, you have already studied something called a velocity field. Do you understand what a velocity field is? This velocity field is defined based on a continuum hypothesis. I mean, people who are, I mean, as a matter of fact, this also comes under microscale fluid flow discussion, is that this, I mean, there are two different concepts you already know. One is Eulerian formulation, and another is a Lagrangian formulation, right. Lagrangian formulation is when you track the particle. I mean, you consider the fluid to be composed of several particles, and you are tracking the individual particles as it proceeds. And in Eulerian formulation, what you do is, in the space you set up, suppose in the space you set up a box, and you try to find out what the velocity of the fluid particles, what is that velocity of the fluid particles that are passing through this block. All right. So, that is what is important to you. That is the velocity that you are trying to find out. Now, and then it is called a velocity field, because you are assuming that the velocity changes in a continuous manner. So, it is not that some particle basically why this velocity is, if you think of this fluid is comprising of several particles. So, some particles are entering, some particles are colliding, some particles are leaving, maybe the number of particles entering and number of particles leaving, there is a mismatch of a little bit, with time it changes. So, all these things are not considered in an Eulerian formulation. In the Eulerian formulation, you consider that there exists a field, there exists a velocity field. That means it is like you have you must have in the first class itself we discussed about this functionality. I mean, when you plot this density, or when you plot any function with the probe volume, and we said that as you increase the probe volume, if it I think that was discussed in the first class itself. If you get the probe volume too small, then you get atomic fluctuations that is affecting the measurements, and if you get the probe volume which is too big, then the mechanism itself, the macroscopic mechanism itself, that leads to a fluctuation. So, your probe volume has to be within certain limit. So, when you make this continuum hypothesis, you are assuming that you have a probe volume, you have a velocity here, you have another similar volume, and the change in velocity from this to this is continuous. So, similarly, you have E which is the electric field in continuum hypothesis. Now, I am sure you remember there is a term called velocity potential, which is referred as phi, and you must have already you already know that this velocity, this potential, it is like it is complementary to something called a stream function, which you must have studied in fluid mechanics. There exists a potential function which is called phi, which is complementary to stream function, which is referred as psi. Now, this phi exists only when del cross V is equal to 0, where V is the velocity field. This exists only if del cross V is equal to 0, and then V is defined as minus of del phi. V is defined as minus of del phi. That is how it is defined. V is, what is V? V is the velocity field. And what does this del cross V means? This is basically curl of a del cross V means curl of velocity vector, and this refers to the vorticity of this velocity field, the vorticity of the velocity field, and if this is equal to 0, then you consider this flow to be irrotational. So, then in that case del cross V is equal to 0, and one of the primary criteria that you have a velocity potential defined, velocity potential will only exist, will exist only if this del cross V is equal to 0, curl of this velocity field is equal to 0, then only, because potential flow exists only if the flow is irrotational. So, this is the so that is how the velocity is then defined, velocity is equal to minus of del phi. All right. So, similarly, in this context of this electric field, we have a very similar concept. In electric field, what you have is you write that delta cross E, that is equal to 0, and if delta cross E is equal to 0, then you have electric field E defined as minus of delta phi, where this E is referred as electric field, which is synonymous to the velocity in our understanding, and this phi is referred as potential. All right. So, just like we had for velocity, we had a similar criteria that okay, if del cross V is equal to 0, then the flow is irrotational, and so you can define a velocity field is equal to minus delta phi. By the same token, if del cross E is equal to 0, del cross E equal to 0 in this in the context of this electric field, or people who work with the physicists who work with electric field, they call this that in absence of a changing magnetic field. So, del cross E equal to 0 means changing magnetic field is absent. So, this under this criteria you can define E as equal to minus of delta phi, where E is referred as electric field and phi is referred as potential. All right. So, with that understanding, what you can write is then delta dot E is equal to rho E L divided by epsa. Delta dot E is equal to rho E L by epsa. Do you remember what we had? What we had for delta dot V? What is delta dot V in fluid mechanics contest? Continuity, right? Del U del x plus del V del y. 0 or change in density if you want to put it. So, here delta dot E is defined as rho E L by epsa, where epsa is constant. No, the epsa is basically the what do you call it, the permittivity, right? Epsa naught into epsa r. You got to brush up your understanding of this electric field. So, this delta dot E is equal to rho E L by epsa, okay. And then if epsa is equal to constant, if this is constant, then this delta dot E can be written as minus of delta square phi. So, that is equal to rho E L by epsa, because that is exactly what we said. E is equal to minus delta phi, E is equal to minus delta phi. So, you can write minus delta square phi is equal to rho E L by epsa if epsa is constant. Okay. So, what you would be writing in that case is, now we have an expression for rho E L, you remember, we have an expression for rho E L charge density, which is this 2 Z E C 0 sine hyperbolic this quantity. This is an expression that we already have. You must have already, you might have written it already on your notebook. So, if we use that, what we end up with is, so what you would be writing in that case is del square phi r, I mean for a general position vector, that is what you would be writing, that is equal to 2 Z, that valence number, elemental charge C 0 divided by epsa sine hyperbolic again Z E divided by kBT phi into kBT into phi. So, that is what you get. So, this is what you get for del square phi r. Now, if you take a Taylor expansion of this sine hyperbolic term, if you take a Taylor expansion of sine hyperbolic term, and you can write sine hyperbolic of u is close to u if Z E and the phi, right, corresponding phi divided by kBt, or let us say Z e. I write this as zeta. I will explain what zeta is much less than kBt. If this quantity is small, that means this quantity, the numerator is much less than the denominator. In that case, you can approximate this as sin h u is close to u. Okay. Now, what is this? Why do I write this as zeta and not phi? What is the difference? What is new here? See, if we try to plot phi versus z, if we plot phi versus z, then you get a profile which is something like this. Okay. This is actually that stern layer that we had. Okay. And then we see that the phi is decreasing like this, and then at z is equal to infinity, this will go down to 0. This particular value of phi, this is referred as, so this is referred as zeta. This value of phi is referred as zeta. So phi drops like this. I have not come up with an expression for phi yet. So I do not know what functional form it has, but one thing I know is that if you solve this equation, you can get, because this del square phi, this is basically, I mean, in other words, it is del square phi del z square. For a 1D system, it is del square phi del z square. So if you integrate this 2 times, you will get a functional form of phi as a, you will get phi as a function of z. But before I solve this, before I get into that expression, I tell you that phi versus z, there exists a form like this. Okay. And at z is equal to 0, not exactly at z equal to 0, I mean here it is, there is a change, I mean here it would be like this, I mean there is a very small layer which is practically negligible, I mean it is difficult to measure experimentally that what is the thickness of this layer. There, whatever potential is existing, that we call, that we are referring as zeta. Okay. So when it came to, I mean if somebody asks, I mean which phi to take, okay, if you want to ignore this, then what phi to take, then ideally you should take the maximum phi that is possible, and that maximum phi is basically zeta. So that is why you are writing it, instead of writing any arbitrary phi at any location, at any, this r is basically the position. So instead of picking up any z and write corresponding phi, you would be writing the maximum of it, which is zeta. So that is how we put the condition z is zeta is much less than kBt. This zeta is referred as it is very famous in many ways. This is referred as zeta potential. Okay, and this thing can be measured. I mean this zeta potential can be measured. There are instruments to measure zeta potential, but that is a different issue. I mean our original aim is to find out what would be the velocity in this electroosmosis. That is what we are heading to. So for that, now we have this del square phi is equal to rho EL by epsa, and del square phi can be written as in with proper the next step would be this, and then sin h u can be approximated as u if this quantity is small. That is what we take. So if that is so, then this would be replaced by this, the sin h would be gone, sin h u would be replaced by u. So what do you get in that case? You get del square phi r, that is equal to 2 z e whole square c 0 divided by epsa kBt phi of r. This is what you get. Okay. So this is also referred as 1 divided by lambda d whole square phi of r. What is lambda d in that case? Lambda d would be lambda d whole square is this quantity, 1 by lambda d whole square is this quantity. Okay. So, then what is the idea here? We have, so you can write d square phi dz square, or for a 1D situation you can write d square phi dz square, that is equal to 1 by lambda d square phi z. That is exactly what you can write. And if that is so, then what would be the solution of this? Solution would be that phi z would be equal to C 1 e to the power z divided by lambda d plus C 2 e to the power minus z by lambda d. See, from this point onwards we have introduced a small z, which is different from the uppercase z that we have been working so far. This uppercase z we have worked so far is that valency number, and the small z now is the distance away from the wall. So, mind take it, make note of it very carefully, and this small z that appears, this is the general solution for phi z. This small z is basically the distance from the wall. So, now you have boundary conditions, and what are the boundary conditions for phi z? You have phi infinity is equal to 0, that is understood. We said that at infinity there will not be any potential, because at infinity you have Na plus and Cl minus in equal numbers. So, you do not have any potential gradient. So, phi infinity equal to 0, and you have the other boundary condition here is phi 0 is equal to zeta. That is already you have, I mean I said that we referred these as the zeta potential. Okay, the potential existing at the wall. So, with these two boundary conditions, if you solve this equation, see, moment I say that phi at infinity is equal to 0, now here at infinity this term will blow up. So, this term you cannot allow this to blow up. So, C 1 has to be equal to 0. So, you are ending up with this expression, and C 2 would be equal to simply zeta. So, you end up with this expression phi z is equal to zeta e to the power minus z divided by lambda d. So, this is the expression that you have for phi z. So, this is how the potential changes with z, okay, e to the power minus z by lambda d. This is a very neat expression you have, very easy to handle, and more importantly, now look at this lambda d term. There is a name to this lambda d term. This lambda d is referred as d by length. What is the importance of lambda d? Can somebody tell me? I mean, can you think about it? You think about it, you have phi z as a function of z, and which is basically, I mean, now we do not consider the Stern layer. Moment we set this boundary condition, we are forcing it to be zeta at z equal to 0. So, we are talking about a functional form of a e to the power minus z by lambda d. So, what is the importance of lambda d now? Where would this lambda d be? Think about it. This d by length is a very important term. The zeta potential and d by length, I think you need to do some study when you go back after the class. You do some study, you find out what is zeta potential and what is d by length. These two are very important concept. So, what does this d by length mean in when you have an expression for potential like this? All right. So, this is the expression, and then you have rho E L z. In that case, what is rho E L z? Rho E L z we had talked about it. What is that? Here we talked about rho E L z. So, if we just multiply by epsa and take the second derivative. So, if somebody wants to know what is rho EL, then what he will do is he will multiply these by epsa into del square phi, that is what it is, that is what we are talking about. So, rho EL z would be nothing but minus epsa del z square phi z. That means, what this term means is basically del square phi del z square. This is a notation a lot of physicists use. Del z, this is basically del square phi del z square. So, basically rho EL z is equal to nothing but minus epsa del square phi del z square. Okay. And what would be del square phi del z square? If this is the phi, this is the expression for phi, then what would be del square phi del z square? You take the second derivative of it, you will be seeing this as minus epsa zeta by, zeta would be there anyway, zeta, you will have a lambda d square because you are taking derivative 2 times, exponential of minus z by lambda d. So, basically it is epsa zeta by lambda d square e to the power minus z lambda d, that is what you get. Now, what we had earlier, we have an expression for concentration profile as well. We had an expression for concentration profile which was like this in terms of phi. Now, if you bring in this phi, here, and before that, if you take these e to the power this quantity, if we expand it in Taylor series, and if you put this phi, instead of phi you put this zeta into that quantity, what you will be getting in that case is C is equal to C0 1 minus plus this z is the valence number E zeta divided by kBt exponential of minus this is distance z by lambda d, z greater than 0. So, this is the expression for concentration profile, and as a matter of fact, this concentration profile that we had obtained earlier, the concentration profile that we had, I mean not obtained, I mean we intuitively we said this is the type of profile we get. Now, you can plot this using this expression. Using this expression, you can plot that concentration profile. All right. So, you have more or less you have some handle over these parameters. Now, this zeta I said that this is a zeta potential. So, this zeta potential is this zeta value, it is a property of the system that you are working with. So, when you pick up a wall, when you pick up an electrolyte, I mean it is this zeta is a property of the system you have. This z is valence number, whether you are working with NaCl or CaCl2, it would be 1 or 2, it depends on that. Kb is a Boltzmann constant, you can figure out what that is. T is the absolute temperature in absolute scale, exponential minus the distance away from the wall, and lambda d is d by length. Now, d by length we have, where did we bring in lambda d? You remember, when you go back to your notes, we were working with this expression. We said that sin h u is equal to u, and we ended up with this expression, and then suddenly from here I said this is equal to 1 by lambda d square phi r. So, if somebody asks you what is lambda d, then you have to write lambda d as square root of inverse of this quantity, right. So, it would be square root of epsa kBt divided by 2 z d whole square C 0, that entire thing under square root, right. So, you know what is epsa, it is the property of the system, kBt all you know, 2 is 2, z is valence number, E is the elemental charge whole square, C 0, where how much is the dissociation, how much ions you you started with, all right. So, this is the C 0, that bulk concentration. So, bulk concentration of ions. So, it is very straightforward. So, you can find out what is the concentration profile. So, you know all the terms here, all right. So, this is what would be the concentration profile. Now, we have solved for what? We solved for just a wall, is there. Okay, the wall for some reason has picked up some positive charge with it, and it is pulling negative counter ions here. Okay, it is pulling counter ions. So, I developed so you have developed a potential phi as a function of Z. You have developed a C plus ion concentration as a function of Z. You have developed a C minus as a function of Z. So, all these things you develop next to a wall. What is above the wall? We do not know. I mean, we are just working with a 1D system above the wall, but when we talked about a flow through a channel, then there has to be another wall above it, right. So, if you bring in that system here, that means for parallel plate geometry, if we talk about parallel plate geometry, where the change is going to be? This equation I do not have any doubt with. This equation will remain same, phi divided by lambda d square. That was the governing equation, right, 1 by lambda d square into phi. This was the governing equation, and this governing equation remains the same. The only change would be in the boundary condition. What was the boundary condition you had taken earlier? The boundary condition you have taken is phi at z is equal to 0 is equal to zeta, and phi at z is equal to infinity is equal to 0. This was a boundary condition you had taken for plate and 1D case above it, 1D situation which is above the plate. But when you have two parallel plates, then there exists a symmetry in between. So, instead of this boundary condition, what you would be taking is phi at plus minus h divided by 2 is equal to zeta, all right. Phi plus minus h by 2 is equal to zeta. What is h by 2? If there are two, if this is the channel, if these are the parallel plates, this distance between two parallel plates, if that is h, so then your z starts from here. This is the place, this is where the z starts from. So, this is equal to plus h by 2 and this is equal to minus h by 2. So, you will write phi instead of phi z equal to 0, phi at z equal to 0 is zeta, you will be writing phi plus minus h by 2 is equal to zeta, all right, understandable. Now, if that is so, then where would be the change in this case? You will have, I mean, what was the general solution we had? Phi z is equal to C1 e to the power z by lambda d plus C2 e to the power minus z by lambda d. Earlier we had this infinity, and to satisfy that we said C1 is equal to 0. Now, that is not the case. In that case, you will have both C1 and C2, and what would be the values of those? If you impose this boundary condition, I think what you will be getting is C1 by lambda d minus C2 by lambda d is equal to 0. Am I right? At well, at z is equal to 0, there is another boundary condition. There is a symmetry at the center, which I have not mentioned. Due to symmetry at the center, phi at z is equal to 0, d of that, d phi dz, that has to be equal to 0, because there exists a symmetry at the center. So, this becomes another boundary condition, another boundary condition here. So, phi plus minus h by 2 is equal to zeta, that is at the wall, and at the center there has to be a symmetry. So, this has to be satisfied. So, play with this, see what C1 and C2 you get. I mean, I can give you the final form. See here since you have e to the power something and e to the power minus something. So, you would be again ending up with, instead of e to the power minus z lambda d that you had earlier, only you have this term, right, only you have this term, and C2 was replaced by zeta. So, that is the only thing you had. Now, you will have is phi z would be equal to zeta cos hyperbolic z divided by lambda d divided by cos hyperbolic h by 2 divided by lambda d. Z starts from the center and goes up there. Okay. And similarly, you will get an expression for rho E L Z. All right. So, this is what you get as a new one. So, what did we have when we had just one single plate and we are considering z running from 0 at the wall to infinity? That time what was the phi z? If I write it here, what was the phi z at that time? Phi z is equal to zeta into e to the power minus z by lambda d. All this z is distance from the wall. Here the coordinate system changed, the z starts from the center, and the expression that we have is phi z is equal to zeta cos hyperbolic z by lambda d and cos hyperbolic h by 2 divided by lambda d. All right. So, look at the change. Now, here this is what we had earlier for simple situation, and this is what we have now because of this boundary condition. The governing equation remains same. Clear to everybody? So, if this is so, then you can come up with rho E L once again. Okay. And once we have rho E L in this case, I mean, you know what rho E L is, how rho E L is related to rho E L by epsilon, how it relates to del square phi. So, you have to take the second derivative of this phi and relate that to rho E L by epsilon and get the rho E L, and once you have this rho E L, then you can use this rho E L in that Navier-Stokes equation. So, you must have seen the thought process here. You have defined a velocity potential, you have to come up with a rho E L, okay, which is basically the charge density, and then you introduce that in the body force term in Navier-Stokes equation, and then only you can come up with a velocity expression for velocity, and then you can say, okay, this is the electroosmosis osmotic velocity. This is the velocity you can expect in electroosmosis for two parallel channels, two parallel plates, channel formed between two parallel plates. All right. So, we will continue this discussion. We have not yet gone to Navier-Stokes, we are just doing the preliminaries. That is all for this class. Meet you next day.